Dependent events occur when a number of things happen one after the other, but the outcome of one event affects the probability of the second or third event. So here's an example of a problem that you'd have to use strategy for using dependent events to solve. A class of 20 students is electing a president, vice president, and secretary. What is the probability that Spencer is elected president, Delaney vice president, and Joe secretary? So there are 20 possibilities to pick from for president. Then there would be 19 left for vice president and 18 left that could be the secretary. But there's only one way of all the possible ways that would be Spencer president, Delaney vice president, and Joe secretary. So the probability of this happening is 1 out of something. We have to figure out what this bottom number would be. And we can do that by saying how many ways can we pick a president, vice president, and secretary out of 20 people, where once you're chosen to serve in one office, you can't serve in another office. So you can say there's 3 slots to fill. There's the president, then there's the vice president slot, and then there's the secretary slot. There are 20 people that could be president. Once the president is chosen, there's 19 people eligible for vice president, and then 18 people that can be secretary. And we know from our study of permutations that the number of ways this could happen would be the product of the 3 numbers. So 19 times 18 would result in 242. If you multiply that by 20, you get 6,840. So the probability that Spencer president, Delaney vice president, Joe secretary, if everybody has an equal chance to be chosen, would be 1 out of 6,840. Let's be a little more formal about how we calculate the probability of dependent events. If 2 events, A and B, are dependent, the probability of both occurring is the product of the probability of A, or the first event, and the probability of B, which would be the second event, after A has occurred. In other words, the probability of the second event is going to depend on what happened in the first event. So if we had some marbles in a bag, and 5 of them were red and 3 of them were blue, and we wanted to know the probability of drawing twice and getting 2 red. The probability of getting 2 reds. Well, the probability of the second red is going to depend on what happens on the first draw. But first of all, to get 2 reds, we have to get a red on the first draw, and the probability of that would be 5 out of 8, because there's 5 reds and 8 totals. So the probability of event A would be 5 out of 8. The probability then, if we take a red out of there, not there anymore, we would have 4 reds, but we would only have 7 marbles left to pick from, because we're not putting it back. And then we're not going to put back the first red that we drew. So then according to our theorem, we multiply these 2 together, we would get 20 over 56. Which there's the probability, but that reduces to be 5 out of 14, lowest terms. So the probability of getting 2 reds in a row would be 5/14. If we wanted to know probability of blue after red, I'm going to get probability of red, then blue. The probability for getting red would still be 5/8, and there's a red going. And then there's still 7 marbles left, but 3 of them are blue, so 3 of them are favorable, and then our probability would be 15 out of 56. I'm not sure you can read that, 15 out of 56. Okay, so what happens in the second probability is numerically determined by what happened the first time. And you can have a string of events. We can say, what's probably getting red, then blue, then red again. And you just have to figure out the separate probabilities and multiply them together. But keeping in mind that you have to figure out how the probability changed based on what happened prior to that.